Hey, this is OXDF, and we're looking at another Hacky Easter challenge. This time it's the one called CodeLocked. This is a WebAssembly reversing challenge, although I think most people, myself included, originally solved it by brute forcing the pin in the DevTools console. So I will show that as well. But the main point of this video is going to be looking at some JavaScript, figuring out how it loads WebAssembly and how it interacts with WebAssembly, and then taking that WebAssembly, downloading it, popping it into Ghidra, and reversing it and understanding how it passed data to and from the WebAssembly. And we'll pull the flag out of there as well. So I think it's gonna be a fun video. We'll learn about Ghidra and how to reverse WebAssembly, as well as we'll do some JavaScript brute forcing at the end. Let's take a look at this challenge. So it's called CodeLocked, and it just says open the code lock at this address, and we will open it. We've got a numerical lock here across the bottom. It's a little hard to see, but it says to clear star, there's 8 numbers, and pound or hash sign to open. And so we can do like put in some numbers here and take a guess. And when it's wrong, I get a nice little, I don't know if you, Rickroll comes blaring out of my speakers here. I can clear it and you hear that kind of slurp noise. And that's basically it, right? So I need to figure out what is the code for this app. I'm definitely going to want to take a look in my dev tools here. Seems like the fastest way to get a look at this. There's a handful of assets over here, but the one I'm interested in here is main.js, which opens up for me. See here, it starts by setting a code string to be empty. We're going to load a bunch of audio stuff. We are going to initialize WASM memory and WASM check to null. I'm going to skip through these functions for now. We'll come back when they're called. And then at the bottom here, I've got this document ready function. So basically, once the assets on the page, the images, the background, everything are loaded, then this gets called. And it's going to fetch check.wasm into response. It's going to create that into an array buffer called file. It's going to call WebAssembly instantiate. So it's going to turn this into a WebAssembly thing that it knows how to execute. And then it's going to get the exports. So this WebAssembly exports some functions. And so that is going to be memory and check, like maybe it's a memory address of a function. And it stores those in these global variables here, and it exits. When I click something, we're going to click this press function. So if I push the pound or the star, which is the delete, it's going to play that slurpy noise, and it's going to make it yellow, and the code is going to get reset to an empty string. If I push the submit or pound or hash sign, it's going to call check WASM on whatever the code currently is. Then the result is going to be message, and if the message starts with a flag, it's going to play success. And I haven't heard that yet, but we will. And then it's going to show this green div, which presumably is going to have the flag in it. Else, it's going to play the fail. That's our Rickroll, and it's going to show some red and alert. It's going to pop up, and the message is going to alert. And then if it's not the submit or the delete, it's just going to show yellow. It's going to play the click sound, and it's going to append the newest number to the code. And then it's going to take the substring so it only has the last 8. And that way it just keeps a buffer of the last 8 numbers as code. So now we really want to focus on what is check WASM. So we're going to read an array of 32-bit integers from WASM memory, the thing called buffer. And we're going to read from 0 to 26. So 26 integers out of memory. That's 104 bytes into a thing called pin array. We're then going to pass pin array as well as the code into encode, which is going to loop over string.length. So the input, that's my input code. And for each thing, it's going to take that value. It's going to create it to a char code. So it's going to convert the ASCII character 2 to the integer value of, let's see, 2 is hex 32, so it's 50, the number 50, and it's going to store that in the array. And so we're going to get an array of integers. It's important here to note, we're not using, so we read this, we just get this stuff out of memory. We don't actually use it anywhere. We just set it here. So at least for the first 8, we're going to just put our value right over whatever was there. It's not clear if we go beyond that. In fact, we can check that out real quick. Let's see. Let's come up here and we will put a breakpoint at this encode, and we will put some 8s in, and we will submit. And now here we have the encode. So you can see our code is all 8s. Our pin array is bunch of stuff. So there's an 89 at the beginning, there's a 110 at the 8th. If we step over in code, and now we look at pin array, you can see all those 56s, so those are my 8th, and then the 110 at the 8 is still there. So we just go for the first 8 things and we write them into this array. And then we have an array offset and an array length. The length is 26, even though we're only dealing with the first 8. We want to keep that in mind. And we're passing that into WASM check, which is the WASM function we initiated earlier. Then whatever comes back, we're going to get the pin array again. In fact, we can play up to here and see what that looks like. Now the pin array is completely different stuff. And if we decode that, let's see, step over that without, that is probably our, let's see, step through. Oh, so now we're down here and you can see our message is, you did not open the lock. So we failed. Can I stop this, or is there some way to stop this without having to, well, we're gonna hear another Rickroll. Oh, we didn't. Sweet. Okay, so we want to look at this WASM. Let's see. So honestly, I like to just come in here. Let's clear out the network tab, refresh this, and come down here. Here's check.wasm. So we fetched it. Here is the URL we fetched it from. I'm going to jump over into a VM now, and we can do a wget on this thing. If we run file on check.wasm, we've got it there. I'm going to open this up in Ghidra. And so let's see, I'll make a Ghidra directory because I like to put my project somewhere. And I'm going to need to do this. There's a plugin that works really nicely for Ghidra. So if we do Ghidra wasm, this is here. And basically what we do is we come over here to the version and or to the releases, and we grab the release that matches our version. Now I'm actually running version 10.3 right now. It's the latest version, but that doesn't exist here. So I'm gonna go ahead and grab this, copy the link, and we will wget that down here. And then I'm gonna, if I start Ghidra and I try to install this in 10.3, it's gonna fail all over the place. So I'm gonna go into op, Ghidra 10.2, I still have on the machine. So we'll do Ghidra run. And that'll open up nicely. Close this. We will need to create a project. So it's a non-shared project. It's not investigation. Let's go to home, CodeLocked, Ghidra, select project directory, and we'll call this CodeLocked. And now we will import file check.wasm. And wait, we got that. Let's see, CodeLocked, check.wasm. And you can see it says raw binary. And that's because I've not yet installed, there is no option for WASM. I've not installed the plugin. So we'll cancel that and we will come over here to install extensions. We'll hit this, CodeLocked, there is our zip. Now it's installed and it says restart to take effect. So we'll do that and we'll run again. And now we've got our project already there. So now when we do import file, we get check.wasm, WebAssembly. It's recognizing there's WebAssembly, and that's awesome. That means we can actually do it. So we'll run this here. The dragon's going to chomp on the bytes for a minute, and we'll click OK. Double click this to get it in the code browser. And yes, we'd like to analyze it. Pick the defaults, and you can see down here it's running. It looks like it's done. I'm particularly interested in exports, and so you can see here there's a bunch of stuff that doesn't look too meaningful, but the check function's there. That's what we're passing stuff to. So we can see the check function takes an array of a pointer to some integers. And I'm going to assume that the interface between the Chrome that I saw before, where it passed the memory address and the length, and this is going to be accepting a memory address, that works out. So we'll call this like code. That's what we put it in. And basically we can see this is not very hard actually. So we need code to be 32. 32, and if you've ever worked with binary ASCII at all, hex 30 through hex 39 is the digits 0 through 9. So I can tell you right now that is the digit 2. And in fact, we can come here and let's start to keep some notes here. Vim code. So we know that's 2. We know the next one, code 1, has to be equal. Well, I keep saying we know. Why do I say we know? I'm assuming, just on a quick glance here, if any of these fail, I end up at call unnamed function 2 on code. But if they all succeed, I end up at unnamed function 1 on code. And so I'm just assuming that's where I want to be. So let's work for that assumption. So now I'm going to say if code, so our first value, we know is 2, plus 7, 9, is equal to code 1. So now we want 9. The next one needs to be code 9 minus 3. So we have a 6. Now here we're going to say, we're going to rename this variable to 6, because that's what we're setting it to. So now code 3 has to be 6. Code 4 is going to be 6 minus 6, so 0. Code 5 is 6 minus 5, so 1. Then we have 6 minus 2, so 4, and 6 minus 1, so 5. So we found the code. In fact, we can, if we can go show that real quick. Where is my, I lost my window. Here it is. Computers are hard. Okay, so let's just do this real quick. 2 9 6 6 0 1 4 5. We don't need these breakpoints anymore, and we got the flag. And triumphant. I want to go further than that. Like let's understand. So we do have the flag. So we know the code. We've solved the challenge. Let's look at now that we know the code. Let's look at how that gets passed to unnamed function 1. And here, all this is doing. Let's see. So we have a couple for loops here. Rename this variable to I. We will rename this variable to J. Arbitrary, doesn't matter. We're going to loop over 26. Matches up what we saw before. Things. For each of them, we're going to have some buffer located at the memory address 470, and so we're going to go I. So when I is 0, it's going to be 470, 474, etc. We have another buffer here starting at 400. We're going to take the value at 400. We're going to XOR it with our input values. This is our code with some math. So we're going to XOR some part of our code with stuff at this buffer for 26 times, and we're going to store it all in this buffer. And then the second loop here, we just do the same 26, and this time we're going to read from the 470 buffer, and we're going to write it back to the initial buffer. So effectively what this is doing is we are going to find values here, and we're going to XOR them by the code. Looking a little bit more closely, we do I plus 4. So we're going to start 4 into the key, and then we mod by 8. So we're going to go 4, 5, 6, 7, 0, 1, 2, 3. 4, 5, 6, 7, 0, 1, 2, 3, all the way through 26. And so that's what we're going to do. We can take a look at memory itself and see if we can actually figure this out. Let's see. Can we go up to 400? Scrolling down. And if we, hopefully, this is all looking like nulls. And here we are right at 400, and we're seeing 4-byte integers. So 58, 54, 06, 05. Let's do some Python here to take a look at this. We'll create a new, make this a little bigger, move around here so we can see it a little better. Okay, so what we want to know is, what I just think I saw is 0, 1, 4, 5 should be the first things we do. So we can do this. We'll say encrypted equals, we'll do bytes from hex. And now we will do 58, 54, 06, 05. Like that. And we can say key equals bytes from hex. And we know this is supposed to be, if we're right, there was 0, 1, 4, 5, that'll be 30, 31, 34, 35. Now we can do zip. What zip is going to do is kind of pair up, the first byte from enc and the first byte from key. And now we can loop over those. We will say e comma k for e comma k in. So that's not a, let's make that something that can be printed. So there we go. So now we've taken these things and paired them together. We don't actually want to pair them. What we really want to do is XOR them. XOR them and then turn them back into a character like this. And right away, we have HE20. So we are on the right path. Rather than do this manually, I think I have key is 0145. Let's go ahead and get the full key in here. So this will be 32, 39, 36, 36. Just pulling these last things here. We can be happy with key. I don't want to type all these in. There's 26 of these, right? So we're going to go, I'm going to guess 470 is where this stops because that's where the next buffer starts. So we'll grab to here. We will copy, nope, we will copy special as a Python byte string. Or a Python list. Python byte string is fine. And now back here we can say enc equals that. That looks good. So now what's cool, there's a cool thing we can use. We can do from iter tools import cycle. And so now when we come back up here, if we did this zip right now, we're gonna get the first 8 characters. We should get the first 8 characters. We messed it up somehow. Oh, okay. We'll have to come back. We'll come back to that. If we do get 8 characters. They're wrong. I'll fix that in a second. Because zip goes up to the shortest of the 2 arrays. So now with cycle, what we can do, if we do cycle around key, that means key will just go forever. It basically just starts at the beginning. When it runs out, it just goes back to the beginning. And so now we'll get that to the length of enc. Now this is still wrong because if we look at enc, we got a lot of nulls in here. We don't want all these nulls. We want every 4th byte. So let's say temp equals I for I in range. Start at 0, go to len of inc, and we're going to jump by 4. And we don't want I, we want inc of I. So what we're going to do here is we're going to say temp is going to actually be, we're going to get basically we're going to go from 0, 3, 0, 4, 8, etc. Through this array, just getting every 4th byte. Len temp, oops, so I close it, is 28. I'm going to say we probably don't want the last 2. The last two are nulls. We want 26 because that's what we've been doing. And I kind of just guessed when I grabbed this out of memory. So now we can say enc equals temp minus 2. So we have enc, cool. Now, come back up here, we zip these together, and we have a flag. We can even do .join with an empty string like that, and we get the flag this way. So that's cool. We've been able to reverse this WebAssembly to figure out how the flag is generated. I did want to show one last thing we can look at with this, and that is, this is actually how I originally solved it before I went in and started diving looking at the WebAssembly. And that is, let's just come here, and we can, come back here and look at our sources, we can call check WASM on a value, right? So we can do check WASM on 1, 2, 3, 4, 5, 6, 7, 8, like this, and we get back the message. We can do this, I mean, if we cheat and we know, if we can remember what it was, if we come back, that's gonna be hard to, okay, yeah, we can do that right here. If we cheat and know this, we can do 29660145, and we get the flag. So but we don't know this. So how would we just quickly check all these? Well, we know there's only 8 digits worth of things, right? So we can do for let I equals 0, I is less than, let's see, 2, 4, 5, 6, 7, 8, I plus plus. Now we can do a for loop where we loop over all the possibles. And we can say, let's see, const padded equals string, pad start 8, 0. So this is going to basically say, if my value is 0, give me 8 zeros instead of just 1. We'll say let msg equals check WASM, and we'll pass in padded like that. That should work. And then we can say if message starts with HE 2023. And I think we do that, yep. And then, so if it's that, we're going to console.log I plus some parentheses there. It's a little bit of formatting. There's our message. And then we will break. Okay, so we're going to do a loop over all the possible pins. We're going to pad out our number to be 8 digits long. We're going to call check WASM, and then if our message starts that way, we will break. This takes about 20 seconds to run. which is like maybe feels like an eternity when you're trying to make a video to show people, but like when you're trying to solve a challenge, like that code took less than a minute to write, well explaining it, and boom, there it goes. We've got the number 29660145 and the flag WebAssembly is fun. I really like this challenge, even though I solved this challenge in 2 minutes originally. There's just so much more to dive into. I love playing with the WebAssembly. I'm glad they didn't give us like a huge mess of WebAssembly to dig through. It wasn't too complicated once you figured out how to get it looking, or in a place you can look at it. So overall, enjoyable challenge, lots to learn. Thanks for hanging out with me till the end. I hope you enjoyed it, and I'll talk to you next time. Bye.